Well, hello. It's very good to be here. I would like to follow up a little bit on what John Smiley did last time. And so I'd like to review just a little bit. John talked about currents. I'd like to recall just what a current is. We're going to be looking at dynamics on C2, and we're going to be looking at currents on C2. And a current, a current is a object sort of like a distribution, except instead of acting on test functions, it acts on test forms. A 1-1 current here acts on 1-1 forms. Thank you. And so what we're going to be interested in is, for us, there are going to be sort of two prime examples of what we're going to use as currents. For us, a key object here for a current is the current of integration. So given any manifold, you would like to associate with it a current of integration. The only problem is you have to be able to take an integral everywhere. So we need to know that it has locally finite area. So for us, the problem of defining a current of integration could be that you have a manifold that is not closed. It just loops back and keeps coming close to itself. So it might not have locally finite area. We're going to be, unfortunate. I mean, of course, currents of integration are a well studied area, and a lot of things are known about currents of integration. If you look in some book like Federer, you find a lot of theorems about rectifiability and the various problems of integration over sets with bad boundaries. Unfortunately, that is all sort of related to the development of when people were studying area minimizing surfaces and the singularities that arose with that kind of thing, and those currents are really not the currents we encounter here. So unfortunately, we just can't go to Federer's book and rip out a few theorems. One standard thing about the current of integration is if you take the boundary of the current in the sense of currents, that's the D of M, you get the current of integration over the boundary, assuming then again that the boundary also is a suitable manifold or suitable set that you can define a current of integration. For us also, it's going to be important to have currents that are positive. For the positivity, we're going to be using the complex structure. And so in terms of some coordinate system, for instance, in the last lecture, John gave you a sort of a short psychological profile of the defects of analysts. One of the defects of analysts is that they, in their native state, tend to revert to coordinate systems. But anyway, here I've reverted to a coordinate system. So if we write this current T as something or other in terms of some kind of basis, and of course also analysts tend to confuse vectors and covectors, but you know, oh well. In this particular case, we can treat a current.
The sentence in Federer's book about that, the introduction.
Yes?
Well, I wasn't going to say this. I thought you knew it.
I don't know it. No.
Well,
Defect of my education. Anyway, we can represent a current as a Hermitian matrix of distributions, and if it's a positive matrix, then that's equivalent to the current being positive, and there is a theorem sort of like the Schwartz theorem on positive distributions that says then the distributions that represent this current, in fact, are representable by integration. So we can treat them as measures, signed measures. And that's very useful for us, okay, because a priori, when you're talking about just general currents, you have the advantage of being able to treat them like generalized functions. You can differentiate them. But when you have positivity, which is a thing that comes in when you use complex structure a lot of times, you in fact automatically get the boost that what was originally a current now is actually going to be treated as a measure. The other thing about our work is going to be when we're working with complex manifolds. A complex manifold has a canonical orientation, and so in other words, you take any vector and multiply it by I. That gives you an orientation, and that means that we don't, when you go to define a current of integration, actually I sort of didn't mention that, I just said here's a Riemann surface. Well, I was using implicitly the fact that to define a current of integration you use an orientation. Given a complex manifold, there is a canonical orientation, so it's not an issue. And so it's, we have positivity. Okay, is this going to not want to stay there? Well. So the currents we're going to be working with are going to be laminar currents. And so what that means is that you, in this particular case here, I've drawn a little piece of a lamination. I've drawn a transversal in red. I have a measure lambda on this transversal, and I can take the thing that I get by just, for each, is that too high on the, for each value t of the parameter, I have a current of integration, and I can just integrate that with respect to the measure lambda. So that's this, that's what this notation means, and that's an object that we want to use a lot, the current, laminar current. So this is an object that comes up in other context, or has a lot of equivalent formulations. If you suppose that you have a transversal family of measures on your lamination, what that means is you have transversals, and on each transversal there is a measure. And if you follow from one transversal to the next transversal via the holonomy takes the measure lambda 1 to the measure lambda 2, and if you go further it takes the measure lambda 2 to the measure lambda 3. So you have a family of transversals, a family of measures. It's invariant under holonomy. This means then that you can use this to write a current that's locally laminar, and this defines a well-defined global current. These are very special kinds of currents, and one of our goals is going to be to show that a lot of things, in fact, that were just a priori currents, in fact, are represented by laminar currents. So our context here is that we want to work, want to apply this to some, the dynamics of polynomial diffeomorphisms of C2. And so, as John had written last time, the attempt here is to be completely consistent with his notation. We're looking at quadratic polynomial diffeomorphisms of...
Can you move it down?
Sure. I didn't know how high. Okay, is that better? So we're looking at quadratic polynomial diffeomorphisms like this, and I refuse to ask myself the question whether it's a good idea to go to complex 2 space. I mean, we should be there to begin with, and we're there, okay? So we're there. And so since the artifact here of being a polynomial means that it's natural to consider the rate of escape. So we have the first coordinate in this representation. The first coordinate's got degree 2. We iterate this thing. The degree goes up. After n iterations, the degree is 2 to the n. That means then if we normalize this way, we have a function that measures the rate of escape. Okay, this we're talking now about some super exponential rate of escape, because we're taking the log and then we're dividing by some exponential factor. So we're looking here at the rate of escape to infinity. Now, it can be shown that this function that you get is continuous, and it's plurisubharmonic. Okay? The continuous, well, I guess it's been discussed already. And plurisubharmonic means it comes about because we're taking log of the modulus of a holomorphic mapping. And let me have one more little picture here to remind you of I'll just put this over here. I think it's after the couple of other talks here. Okay. So the dynamics in the large of a polynomial diffeomorphism are sort of schematically described by looking at the set K plus, The set K plus is the set where things stay bounded in forward time. Here, if I normalize, in other words, if we look at this polynomial diffeomorphism, if we take the Jacobian determinant, just looking at the formula here, you can see you get A for the complex Jacobian. So the volume increase or decrease is a constant. So it's going to either increase or decrease volume. You can multiply it by modulus of A squared. And we can replace F by F inverse if necessary to make sure we don't increase volume. And so in that case, Friedland and Milner observed that J minus and K minus, in principle, K minus is everything that stays bounded in backward time, but in fact that set cannot have interior, so it's equal to its own boundary. The set K plus of things that stay bounded in forward time, that's an interesting set. Its boundary is J plus. So the notational thinking here is that these are supposed to be like, at least the person that, I guess, I'm not sure whose notation this is, maybe Hubbard. The J's look a little bit like the notation for Julia sets. The set K is a compact set that's bounded in forward and backward time, and the set J is the intersection of the J plus and minus. And for us, I don't know if you can see here at the very bottom, we're going to be interested in knowing whether or not these sets J plus or minus could carry laminations. And that's one thing. For us, we're also going to be interested in the current view of this. So if we take DDC of G plus, we get a current mu plus that's a forward invariant current. You can see by the formula, if you take G plus, if you compose it with F, okay, just look in this formula, if you compose this thing with F, your answer multiplies by 2, just because this number down here is off by 1. So if you take mu plus and pull it back by F, it multiplies by 2. So we have a nice current. I want to pull it back. This is an opportunity for an endlessly long conversation. At least Smiley and I have discussed for like infinite length of time whether you're pulling or pushing. But anyway, if we compose G plus with F, then we're pulling G plus back. And that's sort of, for us, what's happening over here. We're taking log plus and we're pulling it back by F to the n. So this is an operation somehow that's born out of pulling things back.
If you pull back G plus and then say dB bar, is that what you mean? That pulls
Yes,
it back?
yes. Mm-hmm. Yes. Here we have the definition of what it is to take DDC. If we wanted to define this as a current, we'd pair it with a 1-1 form. Okay. What we would do here, just for the definition, is just integrate by parts. So we take G plus, a continuous function. We take DDC of phi. That's a form. That becomes a 4 form. We can integrate it, and we'd have something positive. So in fact, afterwards, mu plus, in fact, is represented by measures. And it's not hard to see that the support of mu plus is J plus. And so instead of studying J plus, we're going to study the current mu plus, which really carries a lot more structure. And it's something you can work with in a much better way. And so a couple of questions we can focus on here is, say, this current mu plus, can you represent that as a current of integration, for instance, on the stable manifold? Somehow is it, you take the global stable manifold of some saddle point, okay, so you're looking at the stable manifold, that's some complex manifold consisting of all the points that are pulled into this saddle point in forward time. So we've got some large thing. Somehow does that represent mu plus? And also, could we give this some kind of more concrete laminar structure? Okay, so that's our plan. Well, I'm not sure it's going to. So one advantage of working with currents instead of just sets is that you have a nice flexible notion of convergence. You just use the same notion of convergence you use for distributions. You put it against a test form and the answer converges. So one use of this here, the theorem is that if you take a saddle point P, well, you know that at a saddle point there's a stable manifold and there's an unstable manifold. Well, suppose we take a little stable disk. So this will be just some relatively compact disk containing P inside the stable manifold. Okay. Now, if we pull this back, okay, now it's a little bit of a perversion, okay, so forgive my upbringing.
Well, because the map is invertible, you can't really decide the question. However, if the map were not invertible, you could decide the question.
Yeah, I mean,
And then it wouldn't be a pullback.
okay, it would be a push forward by F inverse. Okay, so we take this stable disk. Well, I won't say any words here. We look at this current of integration. Okay, we normalize it by dividing by 2 to the n, and we get some constant, positive constant multiple of the current mu plus. And so what this gives us, then, we know that the support of mu plus is exactly J plus. So we also know that if we take any stable disk and pull it backwards in time, just pump it backwards, we fill out the whole stable manifold. So that tells us really that the stable manifold is dense in J plus. Okay, this was a result that was conjectured by Hubbard at one point, and this turns out to be true, that if you take any saddle point, the stable manifolds are dense. And in some sense, okay, just loosely speaking, we're sort of taking a current of integration over more and more of the stable manifold, but we're also normalizing it by sort of smearing it out. We're just sort of multiplying it by a number that's going to 0. So in some halfway sense, we're sort of representing mu plus as a current of integration over the whole stable manifold. Okay, so that's the use of the stable manifold. We also have invariant measure. Okay. That want to stay there. Now the stable current mu plus, when we apply F multiplies by 2, if we apply it to mu minus, so I didn't mention it here, but this was all for iteration and forward time. We have a diffeomorphism, so we could do the same thing in backward time. Okay, we could look at the rate of escape to infinity in negative time. We would define a green function g minus, and we'd get a current mu minus. Okay, so we just reverse time and we get the same things minus. And so if we operate on mu plus, that multiplies by 2. If we operate on mu minus, that divides by 2. So formally, this thing is invariant. Okay. Now, how do you compute a wedge product here? Well, the feature that we're using is that it's a positive closed current. Okay, it's G plus is plurisubharmonic, so DDC of G plus is a positive current. D, of course, means that it's going to be declosed. The fact that, so for a definition, what you just like to do is the usual thing, integrate D and DC by parts. If you do that formally, it goes all the way over to phi. And so down here would be the definition. And the definition will actually work since G plus is continuous, which means it's always going to be integrable. So no matter what your, so this is a current, so this is represented by measures. So we need to make, this is going to be represented by measures. We're wedging with something smooth. And we need to know that G plus is measurable, so knowing that it's continuous will do it for us. Okay, so that is the sort of the analysis version of how you wedge two currents together. So if you have DDC of a continuous plurisubharmonic function, you can wedge two of those together just by this formula. You can see the way I've written the definition, it's a little bit asymmetric. I sort of pulled my DDC off of the G plus. Well, if you work at it with not much effort, if you pulled it off the DDC G minus, you could do that too. You get the same answer. Okay. Now, just for the purpose of comparison, in the previous thing we said that that these currents converge to mu plus. So these things are converging to mu plus. Now, how would you wedge these things? Well, if you take currents of integration and wedge them with each other, you get the current of integration over the intersection. So it's a intersection product. And here you get a discrete intersection. Well, assuming you get a discrete intersection. I forgot to write it up here. But if these two happen to be the same manifold, the intersection of a manifold with itself, that intersection product just is defined to give you 0. Okay? Another one of these sort of unsatisfactory situations. But Anyway, here, if you have a discrete intersection, then the current of integration over a finite set, or a discrete set, is just the sum of point masses over those points. Now, a slightly, rather considerably more difficult theorem to prove is that, in fact, we know that this converges to mu plus. We know that normalized correctly. That one normalized correctly converges to mu minus. In fact, we can sort of take the limit inside here and say that the intersection converges to mu. So we're saying that the intersection product commutes with taking limits. That's a theorem here. And so the point of this is just to illustrate the use of working with currents or measures. In this case, we have some measures converging to mu. So what that tells us then is if we look at the measure mu, it corresponds to, defined this way, to a certain way of taking the intersections. You take a stable disk, you take an unstable disk, you pump them forwards and backwards, they start intersecting. That distribution of intersection points gives you the measure mu. So in particular, you get the fact that given a point P, given a point Q, the stable manifold comes out and intersect from P and automatically has to intersect with the unstable manifold through Q. And furthermore, you know how the intersections are distributed. Okay. All right. So let me just mention here that we know that the mu, the measure mu, was defined as the intersection of a couple of currents. It follows that its support lies inside the intersection of the supports of the currents. Okay? And that's defined as being the set J. It's a problem that seems to be not so easy to settle is if these two things are actually equal. So we know, for instance, in the case where the mapping is hyperbolic, they're equal. Just as an example to remind you that you don't necessarily automatically just stumble into equality here. If you take the current of integration over some variety, wedge it with itself, you get 0. Also, if you take the current mu plus, wedge it with itself, you get 0. And so you don't a priori have any reason to expect, you just know that in general a couple of currents, the intersection of the supports is not the support of the intersection product. This object, the intersection of J plus and J minus, seems to get the letter J.
But if you knew they were laminar, that would be true?
Well, actually, even if mu plus is laminar, okay, in the hyperbolic case, mu plus is laminar. If mu plus and mu minus.
Who were laminar current in the sense of your other definition? Would that apply? Probably, right. If they were laminar and transversal or something, it'd be in great shape. Right, you'd be in great shape. The problem is, even if they're laminar, they could start, I don't know. I think you get some zeros.
Yeah, you could, a priori, you could have trouble. Anyway, this is sort of taken the name J. Support of mu is also a pretty interesting object. In the previous talk, it was shown that the saddle points, the closure of the saddle points is the support of mu, and I've just now mentioned that if you take any P and Q, the heteroclinic intersections, their closure is also the support of mu. The support of mu would be pretty interesting, or is a pretty interesting set, pretty natural, important set related to the mapping. Okay, we saw this picture last time. Okay, this is a picture. If your mapping F has the parameters right, so it's generating you a real horseshoe, you get pictures on this side of you, J minus, going this way. Horizontally, going vertically, you've got J plus. If you look at this carefully, you see, wow, this really looks like a lamination. The only possible problem to being a lamination, if you look right there, you got some switchbacks, so your local coordinate box wouldn't make it look locally like a product. Here you've got another problem. But the problems where you have things switching back, those switchbacks sort of wander off to infinity and don't get in your way.
Another picture that you saw, I think, was this one. Here's a more... so here, the idea is you look at this picture and you see everywhere you look, it looks like things are sort of laminar. But if you look more closely, you have a picture like this. Okay, you've got a lot of things going across very nicely, but then you get things switching back. Okay? And you get things also switching back smaller. And the little dots here mean you could have switchbacks thinner and thinner and thinner. So if you look at some point like this, you really don't have a local product structure. Okay? Over here, you could sort of take your box and have a local product structure here, but down here, you've got these things getting thinner and thinner. You don't have it there. Okay? Now, so you just naturally have a problem to deal with. Here is my pitch for why we did the right thing looking in the complex C2. When we're looking at these as complex manifolds, okay, so I've drawn them like this. The curve looks like z equals w squared, so this is a singularity in terms of projecting down this way, but in fact this is a smooth manifold. Okay, just the singularity is a singularity for the projection. If you look at something like this phenomenon, you have a singular projection and these things get thinner and thinner. These things in the limit converge to twice a disk. Okay? In other words, the multiplicity is positive and it goes to 2. If you look at the real analog of this thing, well, if you're looking at currents of integration, you have a orientation here and an orientation there that are going in opposite directions. So when you go and take the limit, you do get a limit, but the limit is 0. So in the real case, you get this, you know, if you're trying to look at currents of integration, the limit sort of disappear, which is, which means that if you're looking at the real case and the complex case, you sort of have different behavior. Okay. However, the thing we want to have here is that our current mu plus should have some laminarity, and it has some laminarity in the sense of measure theory. Okay, so back at the beginning, I showed the picture of what a laminar current is, and very closely related to the definition of a laminar current is that it's equivalent, I don't know if I get that to stay, it's equivalent to have a transversal family of measures. Okay? And so in the case where we have the current mu plus, we automatically get, in terms of current theory, you have slice measures. Okay? You can take this current and you can slice it by any complex transversal, any complex manifold, and you get some slice measures. So you automatically are given, so I mean, we're in the situation where just, you know, we sort of stumbled in. We were given a Flory subharmonic function. We took DDC of it. We get some nice positive closed current. And that, since G is a continuous function, we can restrict it anywhere we like. And that restriction varies continuously. And we can define slice measures. And also, this, just for free, I should have had a plus on top of the G. It's a G plus here. This is also the sense, since G plus is a function that's harmonic outside of K plus, this is harmonic measure. Okay, so it's a familiar measure, good measure. Okay, now it turns out that the current mu plus does have a laminar structure in the sense of measure theory. The measure theory approach is like this. Suppose we're looking inside of C2 and we project down, say, to the x-axis, the complex x-axis. We, say, fix a unit square, Q tilde, and we want to say that we have laminar structure, so we divide this into a lot of subsquares. Okay, so we subdivide Q tilde into a large number of subsquares. And to say that we have some laminar structure just over any particular subsquare, we're going to get, the statement of the theorem is that there are a lot of complex images of, you know, complex graphs up above. We have some transversal measure, lambda sub j. We make the laminar current, and we get something that, as we subdivide more and more finely, this thing that's a sum of laminar currents increases up to mu plus. Okay? And this nature of convergence is pretty good nature of convergence, because what happens here is we can just take any particular subdivision of the unit square,
we can refine that subdivision, and so as we take the limit here, all we're doing is throwing in more and more stuff. We're just maybe filling in, filling in more of these manifolds. And the thing is here that the pieces of complex manifolds that make up this laminar structure are pieces of stable manifolds. Okay. Let me sketch for you how the proof goes of this. Okay. Last time we saw that if you take, say, the x-axis, we could take any algebraic variety. You look at the preimages of the algebraic variety. Well, if this is our particular x-axis, the x-axis is given by where the projection to the second coordinate is 0. So to take the preimage, we just take the second projection to the second coordinate composed with f to the n. It turns out that if we project it to the first coordinate, we get something of degree 2 to the n. Project to the second coordinate, we get something of degree 2 to the n minus 1. I just chose the second coordinate because I wanted to project down. I wanted to have my picture going this way, not sideways. And that's why I have the 1/2. But this does converge to 1/2 of mu plus. And so we want to look at the convergence and find that when we get the thing that converges is going to give us a lot of laminar structure. Okay? So what we do is we divide our unit square into subsquares and let each of the subsquares have area little a. Okay? Now, so we have this blue thing is a piece of an algebraic variety floating around in C2. Its mapping degree coming down is 2 to the n minus 1. Now, what we want to do is construct as much of a lamination as we can, and the lamination is going to be made out of graphs over squares. Okay? I mean, locally over each square, we want to see how much of this is like a discrete lamination above. You have a bunch of analytic functions giving graphs up there. And we're in good shape except where there's a critical point. So if there's a critical point, that's where the red star is. Okay? So the red star is where there's a critical point. We throw that one out. Okay? So the point here is that the number of critical points is the mapping degree, minus 1.
Throw that leaf out or the entire column?
I throw out that, okay, what I do is I slice this thing up. In other words, I look at this as being sort of like a cookie cutter, and I just vertically just slice everything by the squares, and I throw out the connected component of that piece up above that contains a critical point. So the fact that we use about complex analytic varieties is we're throwing out, if we have to throw out that red point, we have to throw out something that has a certain area. The area is essentially the mapping degree. Okay? In other words, the branching order here is going to bound the area, so it's going to be the area down below, which is just little a, times the branching order. Okay? And the total branching order adds up to, well, here I said number of critical points. I meant critical points with multiplicity. So that's going to be 2 to the n times the area of whatever square you're over, and then times some constant c that's just related to the sort of the general size that we're bounded in. So c is just some structural constant depending on the coefficients of the mapping. Okay? So what this means is if we throw out all the branch points, the stuff that is left over is just consisting of good graphs. So we have a graph over a disk, and we have the good graphs. So that's the good part of this current. And so what is this? This 1 over 2 to the n is the normalization. A, let me see now what. A is, right. So how many of these little squares do we have altogether? Basically, the covering order is 2 to the n, and 1 over a is the number of squares in the base. So this is basically the number of squares there is altogether. This is what we have to throw out, and then this is the area of the square. So the area that we're left over with is basically 1 minus AC. So if we make a very small, we basically have kept almost all of our area. And so the point is that then as n goes to infinity, we're left with just a whole lot of graphs of analytic functions giving us almost the whole area of our whole current, and so we just can pass the limit with normal families and we get a lot of laminar current up above. Okay. So that's sort of how this proof goes. Okay. There's one last thing we'd like to know here. If we've got laminar structure, okay, so I guess my pen here is covering up the picture. In other words, we can have, if we want to get almost the whole current mu plus, just by removing a little bit of stuff, we've got all these sort of laminar pipes that give us almost the full mass. We could take the intersection product, okay, we could take the intersection product geometrically. Okay, before I told you how to wedge analytically, here we could also take a geometric intersection, and what that would mean is that if we have an m plus s, that comes over here and intersects with m minus t in this circular point. And so if we take the intersection and we just multiply, we get the product measure, and then we get the point mass at the intersection. Or, you know, if it's more than one intersection, we just get the point masses at the intersection points. Anyway, the problem here is we could have a lot of, a priori we could have a lot of, a priori we could have a set of manifolds that coincide, so we could get a lot of zero when we're taking this intersection product. Okay? But that's one reason that for certain purposes, for us, it's a little easier to actually work with these laminar currents, okay? Because the measure lambda plus is a little bit forgiving. Okay? It forgives things a little bit because even if it were the case that one of these manifolds would coincide with one of those manifolds and we'd have a zero intersection product, which is bad for this because it represents a discontinuity, that still is going to only occur on a set of measure 0. Okay, so having these lambdas in there is essentially taking a current of integration and in some sense mollifying it. You're sort of smoothing it out. You're considering a whole continuously moving family of manifolds, and you're sort of smearing it with respect to a measure. So if a number of these things give you bad intersections, meaning they coincide, if that's just happening on a set of measure 0, you're okay. Anyway, so the theorem here is that, in fact, you can take, so you have a laminar approximator to mu plus. You can do the same thing and have a laminar approximator to mu minus. The geometric intersection product, in fact, gives you the good invariant measure. Okay, so this is good news and bad news. It is something that holds for all cases, for all mappings, but it is not completely satisfying because it's not really laminarity that we're getting. We're getting something usable, but it's measure theoretic, and you'd like to. It would be good to see if for some families, some nice natural families of mappings, you can, if things are actually better than that. So just to recall, when you're looking at one-dimensional dynamics, there is this dichotomy into the mappings that have connected Julia sets and disconnected Julia sets. And in one variable, the Julia set being connected is equivalent to the critical points all being inside of K. And also, if you're going to be looking at the complement of K, that is equivalent to saying there are no critical points in the complement of K. Okay? And so the plan for the next 20 minutes is to make a few remarks on what's happening here in the analogous dichotomy in 2 dimensions, what goes on there. Okay? So the first observation here is I showed you this picture of the general
So I showed you the picture of the dynamics in the large, just sort of the schematic. And so it's a question of what is the natural generalization of the complement of k. So the complement of k, those are all the points that go to infinity in forward time. Okay. So in two variables, you have sort of two things you might think about. You might say in two variables, the analogous set to complement of k might be the complement of k plus, but in fact it seems that the better thing to do, well, the complement of k plus, that's the set where g plus is bigger than 0. Okay, so these are the things. G plus measures the super exponential rate of escape to infinity. So the set where the rate of escape is positive, that's points that go to infinity. It turns out in one variable, of course, if you have any point and you iterate it backwards, of course it comes into, all the preimages come back towards k and stay bounded. So for our case, it seems that what we're best off studying is the set J minus plus, which is just the set of things with bounded backward orbits and escaping forward orbits. So this is a picture you saw briefly last time. So this is one version here. Okay. So this was the interior of k plus. You could maybe have a sink, J minus, okay, and we would be looking then at all the points of J minus that are outside of k plus. That's the set we want to look at. Okay. Now when we saw Hubbard's talk, he spent some time discussing the foliation that's generated by G plus. I don't know if you can see that. The function G plus is a pluriharmonic function where it's positive, and when x is large and y is not large, it looks like log mod x. Okay. So in this region, okay, when you're looking at something like log mod x, that's the G plus, you can find a harmonic conjugate that has a period of 2 pi, and so we have an analytic function phi plus out in that region. Okay, so we have a holomorphic function, and in fact, since G plus is pluriharmonic on this whole region, in fact, you can analytically continue a harmonic conjugate, but it might be multiple valued. So it's analytic in some particular set out near infinity. It has a very, on the whole set where G plus is positive, it has some sort of analytic continuation. If we wanted to find the foliation, we could also take round D of G plus, and that would be a holomorphic one form that would define a foliation. For us, at the instant, the thing is that if we're looking over here at the level sets of G plus, we can look at a tangent vector tau that would be tangent to this foliation, and we could look at some other complex vector xi that's transverse to the foliation. And the important part for us here is that as n goes to infinity, if we're looking at how the differential is acting, the differential takes this transverse guy, it grows at a super exponential rate, but the tangential guy goes to 0. Okay? In forward time. So I was mentioning that the connectedness of J in one variable was related to critical points. So in two variables, you want to know what is a critical point. So one way of defining a critical point, well, maybe I always speak too quickly. We have to be a little careful. When you're defining critical points, it sort of makes a little bit of difference where you're working. Okay? So in the talk that Hubbard gave, he defined critical points, or a critical locus. Okay? And his critical locus was out here in the complement of k plus and in the complement of k minus. So his critical points are out here. Okay? That's what he defined. Here we're talking about inside of J minus and outside of k plus. So we're talking about here in this region. okay, in the set J plus minus. So we're going to try to define what a dynamically, so we're talking about dynamically critical points. And so we're going to define them in this set. Of course, you might also ask what are the dynamically critical points in the set J. Okay. So I can save you asking because I don't know the answer. But inside of an unstable manifold, okay, so we're going to be out here in the set where G plus is strictly positive, we can define critical points, and those will be the points where the unstable manifold basically folds back. Okay, so we have some sort of folding behavior, and the way we measure folding is we use the level sets of G plus as sort of our observational pattern, the grid that we look at it against. If it folds back, then that's a critical point. And the precise point of tangency, that's the critical point itself. Okay. And also that corresponds, if we take the tangent vector tau, we have a vector such that if we take the forward iteration of f, the differential takes it to 0, well, it takes it to 0 in both forward and backward time. Okay. So let me look a little bit more precisely at this. If you have a saddle point, okay, you can look at the stable manifold. It's uniformized. It's a Riemann surface, so it has a uniformization. It's a simply connected Riemann surface, so its uniformization would either be by, well, it can't be compact, so it's either going to be by C or by a disk. It turns out the uniformization is by C, by a complex plane. And we can, if we're looking at a mapping, an embedding of C into C2, it's uniquely determined up to you can reparameterize it up to an affine change of coordinates, but here we're going to make it so that the origin goes to P. And if lambda represents the multiplier at the unstable multiplier at the fixed point, then we have this functional equation. If we take the parameterization psi, and if we take the scale out the parameter zeta, then that's the same as applying f. Okay? So we're going to be interested in pulling our work on the unstable manifold back to C, and that means then we can take the function G plus, pull it back to complex plane via the mapping psi. One thing we get out of this is we can draw a computer picture of the intersection of an unstable manifold by K plus. Okay, and let me see. This is I can have two of them. I guess maybe this is Hubbard's sentimental favorite, so I'll show this one here. Okay, so this point right here is the origin. Okay, and we've got the level sets of the green function drawn like this, and then this is the slice. Okay. What I've drawn over here is the possibility. Here's the origin. I've drawn some level sets of the green function. If this is not connected, we've got some good possibilities for critical points. This would be, if you draw this picture, this allows you to see critical points. Okay. Now there's a theorem here, okay, which gives maybe some criterion here that allow, or several criteria that allow you to decide when you're in the case where the Julia set is connected. Okay, so we first we have some equivalent conditions, but let me just put this over here. One is that J is connected, but
most of the other, well, all the other conditions are like, say, having to do with unstable manifolds. So what we do at the beginning is just replace f by f inverse if necessary. We want to assume that we're not increasing volume. Okay? Then, if you take a saddle point, the slice by the unstable manifold, if you look at the green function, right, so if we look at the set where the green function is positive, the unstable manifold has no critical points. That's one of the conditions. So here I've drawn a case where, just by the picture, you see that J cannot be connected, because the slice by an unstable, I mean, it's a theorem that that's equivalent to J being connected. Okay, so we're taking slices by unstable manifolds, and sort of one of the basic things about this theorem is that you can inspect J very effectively just by drawing this picture. Okay, and this is a pretty reasonable computer picture to draw. It's not a very hard thing to.
So if it's not connected, you can see it.
If it's not connected, you can see it. Yeah. Another version is here that for a saddle point, okay, this thing has no compact component. Okay. Now, and sort of condition 3 I restated down here in a slightly more aggressive form. If there is some saddle point P, and if when we look at the complement, okay, so of course having no compact components means that all the components of the complement are going to be simply connected. This just says, you know, there's some saddle point, and one of these components is simply connected. Yeah, it's equivalent. And the last thing is we had this function phi plus that was defined out near infinity, and the condition is that it can actually extend continuously throughout J minus plus. Okay. So this is in some sense, this is like a monodromy problem for analytic continuation of phi plus on J minus plus. Okay. Now, let me put this over here. Would give you more of that, but I don't think it's going to stay. Now, the connection with laminations is that in case J is connected, okay, in case J is connected, this set J minus plus, the set here where things stay bounded in negative time and go off to infinity in positive time, in fact, it has a Riemann surface lamination. Okay? And, well, it's no surprise, but anyway, but the function G plus has no critical points. The function phi plus, okay, since it's, phi plus has a continuous extension, sort of by topology, that means also that you can make an analytic extension. So I'm going to take the analytic extension from phi plus out, phi plus is like this Butcher coordinate out infinity. We can extend it in through M, and this then is a covering map. Okay? And each leaf is dense. Condition number 5, the set J minus plus has a unique lamination. Is a little bit stronger than that. If you have any little piece of a complex disk lying inside of J minus plus, it has to be a piece of this laminate, or lie inside one of the leaves of the lamination. Okay, so at the end here, I'd like to give you just an idea of how you will prove this theorem. Okay, I would like to give a sort of a sketch. Okay, so how do we get the existence of a lamination? Okay, we have a lot of equivalent conditions. Okay, we have several. That's not the. I was going to go to the theorem. So the equivalent conditions in the theorem, there are various equivalent conditions. I want to use the condition that there's a simply connected component. Okay, and I want to work with this simply connected component. Okay. So here I am. I've got a saddle point P.
And I'm looking inside, I'm just treating this stable manifold as a copy of C, and I'm looking over here where we intersect with K plus, and the complement is simply connected. Now, we pull back the function G plus, and on this copy of C, we've got the subharmonic function H plus. H plus is harmonic where it's positive, and it's 0, so H plus comes down to 0 here, right there, comes down to 0, and elsewhere it's positive. And okay. So what we'd like to say is that H plus on this open set, as you go to infinity, it has exactly one way of going to infinity. It has only one asymptotic way of going to infinity. Okay? Now, before we prove the claim, the first observation is that H plus psi satisfies this functional equation, namely psi of lambda zeta is f of psi. Okay? And then G plus multiplies by 2, so when we look at these, I guess I forgot to mention, when we look these slices here of the unstable manifold with K plus are a little bit different from Julia sets in the sense that they're self-similar. Okay? The functional equation tells you, in fact, you've got this multiplier lambda, and this thing is just plain scales out by lambda, self-similar. The fact that H plus has this functional equation means that it can only grow at a certain rate. It only grows like a power of zeta. That's zeta to some power m. Okay? Now, I'm looking here at some simply connected set. I'm looking at the complement of the black. Suppose I could go off to infinity this way and have a different way of going off to infinity, I have a path going off to infinity, and along that path H plus goes to infinity. Suppose I've got like a different path out here going to infinity, and suppose H plus is going to infinity along that path. Okay? Well, then, using the fact that this whole picture is self-similar, I've got, well, this path here goes out along some sort of alleyway. That path goes out along some alleyway. And then I've got, since it's self-similar, I have narrower and narrower alleyways along which this harmonic function goes to infinity. Okay? But the Fragment-Lindelof theorem says that if you have some bound like this, and if you have some function, you know, if it's 0 on the boundary of some angle, and on the interior you have a bound like this, bound by a power, if the angle is narrow enough, that means the function has to be bounded on the interior. So if these are narrow enough, the number m is just a fixed number here. If these things are narrow enough, that tells you that the function has to be bounded along there. Okay? So, in fact, we only have one way of going to infinity. Okay? So what does that tell us? That tells us that if you only see the simply connected set O is the same as the unit disk, what that tells you, it gives you sort of a devious way of saying that this function phi plus on that open set is in fact the universal covering map. So what that means then is that, remember I was saying that the condition of having no critical points means you have no switchbacks. So when you look at components of the unstable manifold, function phi gives you a nice projection down to some open set. You can lift that projection and get all these nice lifts, and these lifts, in fact, we already saw that the unstable manifold is dense, or stable manifold is dense in J plus, unstable manifold is dense in J minus. So all these, you have an infinite number of pieces up here. They're all given by graphs of analytic functions. You can take the closure, and that lets you have a lamination. So that's the sketch of the proof here, that when you're in the case that J is connected, you in fact do have in the set J minus out where G plus is positive. Out here, J minus then does have a unique Riemann surface lamination in it. So that's everything. Thanks.
How do you determine this lambda measure for the lamination to obtain the current?
Oh, that's the slice measure of the current U plus.
So it just, I mean, it's from the Minicourse or
Yeah, it just comes out from the limit process.
But you could say you can count the number of times the algebraic variety or the thing that you're using to generate cuts through the slice. You get a bunch of points. Right?
Yes.
You can define that.
Right.
Geometric description, right?
Let me see, are you talking about the one where you got the laminar structure for the current? So I guess the only problem is you have to throw out a certain number of right, you throw out a certain number of pieces and everything that's left, that gives you a laminar structure. That defines the transversal measure.